Right, so we're going to have a discussion on Fluidity. That's another open source code. Uh, so we already have a virtual machine like for the other codes as well. So I'll start the virtual machine, and the first thing I'll do is I'll show you a manual. Again, this virtual machine is available with us. If you want, you can. The software is available on the internet. You can read the instructions and download it. If not, then you can always use this virtual machine if you want to run a quick code without spending time on installing it. But it's quite easy to install. Let me increase the size a bit. This is fine. Right, I think that's big enough. So what we'll do is we will look at the installation. So what I've done is I've downloaded the software from GitHub, and this is how it looks. So there's a manual folder here. I can go to the manual, and then here there will be a file called Fluidity manual. It may not be there. You have to compile it from a LaTeX file, but that's okay. If you do it, you get this manual. It's a large manual with 300 plus pages. It has instructions about how to install it, how to run it, what are the equations, and so on and so forth. So it has a complete, it's like a complete manual for a software. Okay, so you can, and it uses finite element method, by the way. That is something we have not discussed as a part of this course, but it can also be used for solving fluid mechanics equations. The ideas of solving fluid flow equations are the same as predator-corrector equation, but when you discretize the boundary terms, which were infinite volume, for example, we used an average and so on. So here we use slightly different techniques to discretize them. But there are specialized courses on FEM in this institute, so you can also take them. Right, so this was the manual. Next is typically what you would do is you would see examples to check if you have an example which is closer to the one you want. So we go to the examples folder, and here we have this list of examples. So I see, for example, there's something called a lock exchange. So lock exchange is a lock in this context is, let's say you have water used for canals, for example. So in canals we have a gate. So that gate is called a lock. So what happens is if you enable the lock, so the water on the different sides can be of different heights. So this is used typically when you have canals at different heights. So what you do is you have two locks. So water level is the same as, let's say, the left. And then if the boat has to go down in the lower level, then the locks are closed, the water level goes down, the boat goes down, and then this is opened, it goes away, the lock is. So this is how it lock works. But lock is simply a gate between two water bodies. So sometimes we have, water at different temperatures. So when you change, when you remove the gate or you open the lock, temperature, because of temperature gradients, there is some flow that develops. Interesting. Okay. So this is what this problem will simulate. So what we do is we just go to the folder. I go to the examples folder, and here I see that there is this lock exchange folder. I do an ls, and I see there are some files available there. So the easiest thing to do is in build systems, there will be scripts already written. So if I see a file called makefile, okay, here this makefile will have some options available. And again, this is something you will learn in the next semester in this AMI 522, where we learn how to write these makefiles so that you can write scripts and all. So we have something called, it says pre-process, run, post-process, and that's typically what you do, right? You do a pre-process to make a geometry and mesh, you run, solve the problem, and then you post-process to generate some graphs and so on. And then you also want to clean it. If you have already run it, you want to make sure that, so it's already run, there are some files, so I'll do a make clean. So that will clean my files. I'm back with the same set of files that I started with. The output files and so on are deleted. Okay. So this enables the user to do things quickly rather than learning to generate the mesh, run the code and so on. So now I'll say make pre-process. So this will generate the geometry and mesh. Then I'll say make run. Sorry. And now it will start running the problem. So now the problem is running. So as a user, I can focus more on the problem I want to solve rather than understanding how to write commands and so on. So this make file build systems are actually quite useful in this context. Okay. So then I'll open, it's still running. So let's open a different window and then go back to this folder. So you can see that now files are getting generated again. So now what I can do is intermediate, I can run paraview. So paraview is the same as what we had earlier for open foam. It's called parafoam, but that's the same thing. So then I open this set of VTU files, and then you can see that this lock is visible now. I would want to see the temperature. So to start with, at t equal to 0, we have a temperature which is very different. Whatever the values are, that don't matter. And then as we proceed, now because of, there's buoyancy, gravity, so the cold fluid will tend to fall down and hot fluid will rise up, but they'll be mixing because of temperature differences. Okay, so these will result in, here the gravity direction could be different, but this will result in mixing and very interesting fluid flow that will develop as a result. Okay, so this is called buoyancy. You have, if you've done heat transfer, you already know about if the presence of gravity and difference in density results in a flow. So this is what is happening. And then I can do all sort of plots that I want. I can plot the velocities. For some reason it's not showing, but usually you will scale is fine. Anyways, and one interesting thing here is that if you look at t equal to 0 and I look at the mesh surface with edges, this is the mesh. So the mesh actually is quite non-homogeneous. It's not that homogeneous mesh that we had, right? It looks quite coarse in this region, and near the boundary, it actually is really fine. I'm not sure if you can see that clearly, but they're very elongated elements. So this is an anisotropic mesh in the sense that it has a directional preference. It is quite fine in the x direction. It has more number of points in the y direction because there is a boundary. So you'd want to resolve this boundary of two temperatures, so you can actually have an anisotropic mesh to start with, but not just to start with. When the problem is being solved, the mesh is modified. You can see as the flow changes, the mesh evolves. So that is optimizing your computational resources. So that will result in you being able to resolve the boundary very accurately. So you can see these structures are resolved very accurately. So we can actually reload, it should have completed. And this is because you have a very large number of mesh elements in this region. But in the region where nothing interesting is happening, it's very coarse. So this is called adaptive mesh refinement or mesh adaptivity. You adapt the mesh based on solution values. So with FEM, you can actually do these things very efficiently. Okay.
सर ये कैसे implement किया हो मतलब जैसे जहाँ पे ये volatility बढ़ रही है वहीं पे fly कर
It's
रहा है
very it's difficult to discuss. It requires a lot of mathematics understanding and so on. But you can think of some sort of an error that is calculated, and we say that the error is much larger. So you sort of scale the error with the gradient of the temperature. So gradient of temperature is large at the boundaries. Right? It's actually not the gradient; it's a second. It's called Hessian. But you sort of scale your mesh size with something called the gradient of temperature. So gradient of temperature is sort of zero in this region, right? It's the same everywhere. So the mesh is coarse, but the gradient of temperature is much larger in this region. So the mesh is fine, and it is fine in the direction where the gradient is large, not in the other direction. So it's anisotropic as well. Okay, so this is so we discussed now. Let's discuss quickly another problem. So now, if you had a problem like this, you could start with this and then play around with the geometry. It uses Gmesh as well, so Gmesh already. Play around with the geometry, mesh, or here you don't need to make the mesh fine because it's already taking care of these things. So many options are available. The next example is something called a dam break problem. Okay, so this is called water column collapse, water collapse. So again, let's make clean. So if I look at the make file, it again has these options called pre-process, run, post-process, and clean, and so on. Okay, so I can do again make pre-process. So it generates the mesh. So now you can see that there is a 2D tank.mesh. So I can open Gmesh and open this 2D tank.geometry. So it shows me this kind of a geometry. And then if I look at the mesh, it shows me a mesh as well. So here we have sort of a structured mesh, but what happens is when the software will run, it will take control of the mesh. So the mesh will get adapted based on the solution. Okay, so I can do a make run. It starts running it again, and while it is running, I can so it has run. I see around 3 files being generated. So now I can run paraview. I can open this. It's not that difficult to use these open source codes. That's the whole idea. Okay. Here I want to look at the volume fraction. So this is a problem where you have water and there is a dam, but for some reason the dam breaks, and now the water is going to enter the region where water was not supposed to be. It's like a typical dam that you have, which a reservoir where a dam wall can rupture. So we do these kind of hazard simulations just to see what sort of effect will it will have. So now you can run it and you can see that the water is going to now splash. It's very interesting to see these. So if it runs for a longer time, you'll see these splashings, sloshing, where it goes up and then falls down. Some air pockets are being generated. And again, this is using adaptive mesh refinement, and that is the reason this interface is being resolved very accurately. Okay. Right. So typically we will have. By the way, this is not a part of the syllabus. If somebody wants to leave, you can always leave. Time is over, but I'll continue with, for a few more minutes just to complete this discussion. If you find it interesting, you can stay. So we had this. Let's clean it again. So we have this geometry file that's available. So I can open this in a text editor. So I'm using Vim. It's much quicker to use that with text prompts. So you can see that we have points, we extrude them to make lines and so on. So it's very interesting. So what I can do is, for example, I extrude it to a length of 3.12. Okay, so that gives the width of the tank to be 3.12. So I can easily change it here. So I can make it, let's say 6. And then when I do a make pre-process, it generates a mesh which will take care of this change that I have done in the text file. So now we can see that this new point is at a distance of 6.1. Okay, so you can make these changes manually, or you can also have a script doing it for you. So let's go to another case, which is called a lid-driven cavity. That is a problem we have already seen. The top lid. In fact, you have solved it as a part of the assignment, right? So first, I look at the make file. Sorry. So it has an option of pre-process, run, post-process, and so on. So here, pre-process, right now it won't make sense. You learn how to use it in the next semester if you enroll for the course. But more or less it tells us that our mesh size is 16, 32, 64, and 128. So you are basically refining the mesh. So typically what you'll want to do is, when you solve a problem, you'll want to do a mesh independent study or a mesh convergence study. So there what you do is, you run the problem for different mesh sizes and see the plot the value at some point and see how the solution is changing with mesh size. So rather than running it manually by changing things, you can have a script like this. It will do everything for you in one go. So let's see. So I do a make pre-process. So it generates 4 folders. So one folder has a mesh size of 1 by 16 all the way to 1 by 128. Okay. Then I have to do a make run. And now what it does is, first it will run for n equal to 16 mesh. Once it is completed, it will run for n equal to 32 mesh. If you had a multi-core machine, you could also write it so that it will run all of them on different processors. So it will check how many processors you have, and it will, once it gets the value from the machine, it will use that many things in parallel. So you can do all these advanced things. Not that difficult as long as you know how to do them. So that makes our life as computational scientists much easier. So if you plan to stay in these kind of roles, then you should definitely do that course in the next semester. Right, so it's still running, but let's look at, so it's running the coarsest one, so that's 16. So it has some files being generated. So here I can plot the velocity magnitude, and you can see that some interesting stuff is happening. But here if I plot the glyphs, they'll be more interesting. Scale it with velocity. So now we can see something. So let's scale it 0.4. You can see that there is a recirculation. Because the lid is moving, you'll see some recirculation happen. Okay. I can also do a make post process. Well, that's not working, but let me show you the make post process for the previous problem, water collapse. So if I do make post process, then it generates these I think I cleaned it, but I already have another one that I ran in the past. So I do a make post process, and that will result in some PDF files being generated. So I can open them in Firefox. So I'm doing things very quickly, okay? But you'll have the video if you want to explore them in your own time. So I can open these PDF files. I already had the experimental data, which is these circles, stored in some file, and now Fluidity is running, so I'm getting some data from the data files. So the code did not complete run till 2.5 seconds, it only ran till 1.5, so I have this dashed line for 1 point. So basically it's a water column collapse, right? So what it does is it has put 2 gauges at 2 different distances in the channel, and it measures the size of water as a function of time. So at this distance of 2.725 meters, initially the water had not even reached there, because the dam broke and the water started to move from left to right. So at around 0.5 seconds, the water actually reached that point. And then you see the water level increasing, but after some time, the water level started decreasing because the water moved further. Okay, so this is, we are plotting this at different times. So you see that we have all this written in scripts. So I can now run it for different cases, different parameters, and I can just run one file and go. And by the time I come back, I have all the results available as PDF, final PDF files for different cases. I simply have to. Now people go to the extent of writing scripts to include them in your presentations as well. So that way it's completely automated. You run the one script, you leave, you come back with a nice PDF, which is actually a PowerPoint presentation, and then you just present it. You would want this level of an automation, right? I mean, if you work in companies, for example, you don't want one person, because people can make mistakes, they get bored and so on. And then if the supervisor or your boss says that, why don't we run it for a different case? You will not get frustrated. Easy, just change the number, run it, and then come back the next day, you have a presentation ready. You can even have an automation where it will send an email automatically when it's done to your boss. It's not that difficult. You have softwares available. In Python, you can easily write those scripts. So once the code is completed, it generates an email, sends it. You're sitting, having fun, playing video games, and the work is done. Except that you'll be doing something more interesting, technically, not playing video games. Video games are also fun. Anyways, so that's the end of the discussion I wanted to have. I don't think there's anything else. How do you change options, right? So in ANSYS, you had these places where you could press buttons. In OpenFOAM, we had a file where we could change numbers. So what do we do here? So here also we have a file, but we also have this software called Diamond, which will read that file for us and allow us to interact with that file where we set the options graphically. Okay, so these are called preprocessor tools. So if I open this FLML, which is basically like an HTML markup language file, so this shows me all the options. So now I can play around with this. Okay, so this we had water, so we had initial volume of water, right, where the dam was. So we had a volume fraction, which is basically how much volume is water, how much volume is air. So here initially we have a Python script which says if your x coordinate is less than 1.2 and your y coordinate is less than 0.6, you have water, otherwise you have air. So you can easily define the initial conditions by using Python scripts in this software. Although the software is written in Fortran, but you can have interaction with Python scripts here. So if I want to have a volume of water which is slightly larger in size, higher in size, I can simply change this number from 0.6, let's say, to 0.8, and then that will have more water to start with. Okay, so this is where you make those changes. You can also have solver settings. So it will have so for example, if I'm solving, let's say, the velocity equation is being solved using linear solvers. So I can change, so this is solver, right? So it's using an iterative method. So there are different options available. Conjugate gradient, generalized residual method, preconditional Richardson method, and so on. So there are different methods available. So you can play around with that. You can change parameters, you can change preconditioners. A lot of options are available here. Depending on what level of user you are, you can play. But it's always good to start with something that works, and then it's called a minimum working example, and then you modify that MWE to the case that you want to set up. So that way, the other options are sort of expected to work. Okay. Any questions?